Hello students, good morning, and today we are going to start the redox titration. So we are continuing redox reaction. This is our fourth lecture of redox reaction. In the previous three lectures we discussed a lot about redox reaction. So this is the final stage of redox reaction in which we are going to apply the concepts of redox reaction to solve the real problems asked in IIT JEE, that is redox titration, problems related to redox titration. So most of the questions in IIT JEE from this chapter comes related to redox titration. So redox titration is going to be the application of redox reaction which we have studied so far. So redox titration. This is our today's topic, redox titration. Step by step, we will try to understand the concepts of redox titration and then we will be applying the concepts in solving problems related to redox titration. The first thing comes here is, what is the objective of this redox titration? Why do we need to know this redox titration? And there starts the study of this redox titration. Suppose a mineralogist who search for minerals in earth has got some sample of iron. Suppose a mineralogist has got a sample of iron and he knows that the sample contain iron in the form of say Fe2O3. So in the mineral the compound is known, that is ferric oxide, but the experimentalist, the mineralogist want to know what is the percentage of ferric oxide in the sample of iron. That is the objective. And to know the unknown amount of known substance in a given mass of sample, we perform an experiment, and one of the possible experiment is redox titration. For redox titration, the compound in the sample must be able to act either as an oxidizing agent or reducing agent. Here we have ferric oxide. So the iron in ferric oxide or ferric oxide in the sample can be known by a method called redox titration. And from analysis of this sample, we will develop the concepts of redox titration. So our job is to determine the mass of ferric oxide in a given mass of sample. In the sample, besides this ferric oxide, there are some impurities also which we will assume that they are inert in redox reaction. They do not participate in redox reaction. So what we do, we first dissolve this sample in H2SO4 solution. Ferric ion cannot be estimated directly by redox titration. So what we do, we add then some strong reducing agent, and that too in excess. Zinc is added to the solution of sample which contain ferric oxide, and zinc is in excess. Zinc is a reducing agent. So what it will do? It will reduce all iron into ferrous iron. It will reduce all iron into ferrous iron, which will come in solution like this. We filter the solution to remove the impurity, insoluble impurity at least, and unreacted zinc. So the filtrate now contain ferrous iron. By dilution, by adding water to this filtrate, we make a stock solution of known volume, say 100 ml. What we do? After filtering the filtrate, we dilute it to make up to mark, and we have a marking of 100. So we have prepared 100 ml of stock solution. So what we have done so far, we have taken a sample which contained ferric oxide. We first dissolved the sample in dilute sulfuric acid, and then we added excess of zinc, which reduced all iron into all ferric iron into ferrous iron. And then after filtration, the filtrate containing ferrous iron is diluted to make a solution of a specified volume. Presently we are taking 100 ml that volume, and that will be treated as stock solution. In the next step, we will be taking a small portion of this stock solution for analysis through titration. We know that ferrous iron is a reducing agent. So to determine ferrous iron in solution via redox titration, we require an oxidizing agent. There are several options for oxidizing agent, but the most commonly used oxidizing agent in laboratory is potassium permanganate. So what we will do next, we will prepare a solution of potassium permanganate which is of known molarity. So prepare a KMnO4 solution in acidic medium of known molarity. So now we have stock solution and a solution of oxidizing agent whose molarity, strength, concentration is known to us. We put this oxidizing agent in a glass equipment called burette, and there is a burettes of different volumes. So we select a burette of known volume which suits to our experiment. So it is burette, and here we have marking in the burette. So starting from 0 to say 50 ml burette we have taken. We fill this burette with potassium permanganate which we have prepared, and then we take a small portion of that stock solution to be analyzed. Let us say we have taken 20 ml of that stock solution. Then we add potassium permanganate drop-wise from the burette. As we start adding potassium permanganate from burette, potassium permanganate is an oxidizing agent and the solution containing ferrous ion acts as a reducing agent. When we start adding potassium permanganate, the reaction between oxidizing agent KMnO4 and ferrous ion will start occurring since the medium is acidic. So permanganate will start reducing into manganese ion and iron will start oxidizing into ferric ion. So this reaction will start occurring. Since we are adding drop-wise potassium permanganate, so the added potassium permanganate will get reacted with ferrous ion and will get converted into Mn2+. We continue this process. A time will come at which the ferrous ion in the solution here will get exhausted. At some or other time, the ferrous ion in this 20 ml sample or solution will get exhausted. The time at which this ferrous ion get exhausted, we assume that this reaction is complete. And the point at which this reaction is completed, just completed, is known as end point. So end point is the point at which the redox reaction involved in titration is just complete. It is the point at which reaction is just completed. We stop the addition of potassium permanganate. So if we detect the end point, if we find out that end point has reached, we stop adding potassium permanganate. And let by that time potassium permanganate is here. So we measure the volume of potassium permanganate, and then what we apply, that at end point the total gram equivalent of permanganate, which will be determined from volume consumed and molarity, the gram equivalent of potassium permanganate used up is equal to gram equivalent of ferrous ion. So at end point what will happen? Gram equivalent of KMnO4 used up is equal to gram equivalent of ferrous ion present. So if the volume of potassium permanganate is measured here, required to reach the end point, molarity is known, using volume and molarity of potassium permanganate, the gram equivalent of potassium permanganate can be calculated, and with that gram equivalent gram equivalent of ferrous ion will also be known, as they will be equal. And then we convert the gram equivalent of ferrous ion from 20 ml to 100 ml stock solution. That will give the total gram equivalent of ferrous ion. And then from the gram equivalent of ferrous ion, we can determine the moles of ferric oxide and therefore mass, and do the calculation for the mass percentage of ferric oxide in this sample. So that is how redox titration work. At end point, gram equivalent of oxidizing agent will be equal to gram equivalent of reducing agent. One more point here is that how we know that end point is reached. Usually end point is detected with the help of an indicator. Indicator is used in all kind of titration, but nature of indicator depends on type of titration. In redox titration, different type of indicators are used, commonly called metallochromic indicator. But potassium permanganate titration is slightly different. In potassium permanganate titration, no external indicator is required. It is due to the reason that potassium permanganate itself acts as an internal indicator. Potassium permanganate itself acts as an internal indicator. How it acts as an internal indicator? Let us know that. We all know that potassium permanganate solution is deep purple in color, and purple color of potassium permanganate is due to this permanganate ion. Purple color of potassium permanganate solution is due to this permanganate ion, and the intensity of color of permanganate solution is so high that even a drop of potassium permanganate solution can make a bucket full of water purple. So it is highly intensely colored, but the color is due to permanganate ion. So had there been no reducing agent, addition of one drop of permanganate would have made this entire solution purple. But that will not happen now. The reason being, potassium permanganate added will be reduced by ferrous ion into Mn2+, converting itself into ferric ion. Ferrous ion, manganese plus 2, ferric ion are all colorless. So permanganate added will be consumed by ferrous ion, so solution will have no permanganate surviving, and therefore there will be no color in this solution. So the purple colored permanganate will get decolorized when added to this solution. We continue adding potassium permanganate. Imagine the point at which ferrous ion is just exhausted. So when ferrous ion is exhausted, addition of one extra drop of potassium permanganate will make the entire solution purple, because there is no ferrous ion left in the solution below to reduce permanganate ion. So that will be the end point. So end point in this titration will be the point at which this solution, which is colorless originally, develop a persistent purple color. So permanganate itself has acted as an indicator, and that is a reducing agent simultaneously. So no external indicator is needed in potassium permanganate titration, and therefore we say that potassium permanganate titration does not require any external indicator. Now let us verify this. Let us understand this by giving some numerical data to the situation. Suppose suppose 3 gram of sample was taken initially. Suppose 3 gram of sample containing ferric oxide was taken initially. So this sample containing ferric oxide on treatment with zinc converted into ferrous ion. That ferrous ion has gone into 100 ml, and 20 ml of that ferrous ion solution when titrated with potassium permanganate, and let us say this potassium permanganate solution is 0.03 molar, and let us say that this 20 ml solution required 40 ml. Say this has come to this level. Suppose this has come to this level and total 40 ml of potassium permanganate is consumed in titration of 20 ml of the stock solution. So to the same situation we have given some numerical values to understand how calculation works exactly. (40 ml 0.03 molar potassium permanganate. So first we convert molarity into normality so that we can apply the concepts of equivalence, otherwise we will have to balance the redox reaction, which we don't want now. So normality of KMnO4 n factor is 5, so it will be 0.03 multiplied by 5.15 normal. So milliequivalent of KMnO4 used will be equal to volume multiplied by normality. So volume into 0.15. So it will be 6 milliequivalent. And 6 milliequivalent of potassium permanganate, 6 milliequivalent of potassium permanganate will oxidize 6 milliequivalent of ferrous ion. So this will also be equal to milliequivalent of ferrous ion in 20 ml. So total ferrous ion will be 6 into 100 by 20. 20 ml contains 6, so 100 will contain 6 into 100 by 20, so 30 milli equivalent. Now we have to convert this ferrous into ferric oxide. So let us convert this first into millimole. It will also be 30 millimole of ferrous ion. It is due to the reason that n factor of ferrous ion is 1 here, plus 2 to plus 3. And the source of this ferrous ion is ferric oxide, Fe2O3, giving 2 ferrous ion. So if we have 30 millimole of this ferrous ion, definitely there would have been 15 millimole of Fe2O3 in sample. So if we convert this for mass of Fe2O3 will be 15 into molar mass, it is millimole. So 15 into molar mass. If we convert molar mass, if we calculate molar mass of this, so 56 into 2, 112, 48, 160 divided by 1000. If we calculate it, it would be 15 into 16 divided by 100, 2.4 gram. So it comes out to be 2.4 gram Fe2O3. If we go for percentage, it would be 2.4 divided by 3. We have taken 3 gram initially into 100. So it is 80%. So the original sample of mineral contain 80% ferric oxide by mass. So this is the purpose of redox titration, to determine the unknown amount, which is 2.4 gram, unknown amount of known substance ferric oxide in a given mass of sample. So now we are going to practice a lot of questions based on redox titration, a variety of questions based on redox titration, and gradually will increase the level of difficulty of problem so that we can understand thoroughly the principle of redox titration. Let us try now a simple problem in the beginning. Let us say 0.1 gram of a mixture, 0.1 gram of a mixture containing ferrous sulfate, ferric sulfate, require 25 ml of a 0.004 molar KMnO4 solution in acidic medium. Determine mass percentage of ferric sulfate in original mixture. So in this question, we have a mixture. So 0.1 gram consists of ferrous sulfate and ferric sulfate only, no impurity. When we go for titration with potassium permanganate is an oxidizing agent and it will oxidize only ferrous sulfate, not ferric sulfate. So first we would determine ferrous sulfate, and then by subtraction we would determine ferric sulfate. So let us see how to determine ferrous sulfate first. Once again, ferrous ion in the mixture will be oxidized by permanganate ion, giving ferric ion and Mn2 plus, since the medium is acidic. So milliequivalent of permanganate will be equal to milliequivalent of ferrous ion. Milliequivalent of permanganate will be equal to milliequivalent of ferrous ion. And milliequivalent of permanganate will be what? 25 into 0.004 into 5 molarity multiplied by ion factor, normality multiplied by volume, milliequivalent. And that would be equal to 25 into 400. So it is 100 into 500, so 0.5. It is 0.5 milli equivalent. Milliequivalent. So it indicates that 0.5 milliequivalent of ferrous ion is present in the mixture. So 0.5 milliequivalent of ferrous ion is also present. And in this reaction, N factor for ferrous ion is 1. So we can say that this is also equal to 0.5 millimole of ferrous ion. And the source of ferrous ion is ferrous sulfate. So millimole of ferrous ion will also be millimole of ferrous sulfate. So this is also the millimole of ferrous sulfate. If we convert it into mass, it would be 0.5 multiplied by its molar mass, and its molar mass will be 56 plus 96, 152, but divided by 1000 since it is millimole. So 152 into 0.5, 76 divided by 1000, so 0.076 gram. So when we convert it into percentage of ferrous sulfate will be 0.076 divided by 0.1 into 100. So it is 76%. So mass percentage of ferric sulfate, which will come by subtraction, will be 100 minus 76, or 24%. So in this titration, we have determined the percentage of ferric sulfate indirectly by titrating ferrous sulfate with potassium permanganate. Let us take one more example of similar type related to fundamentals of redox titration. Suppose a situation is given in which 25 ml sorry, let us take 45 ml of an acidic potassium permanganate solution is required to oxidize 50 ml of a ferrous sulfate solution. What volume of the same KMnO4 would have been required to oxidize 25 ml of the same FeSO4 solution had the basic medium been used. Now it's a very fundamental question, change of medium. The concept is how to manipulate the change of medium. So in one experiment, ml KMnO4 oxidizing 50 ml ferrous iron. In another experiment, say X ml KMnO4 is oxidizing 25 ml ferrous iron, and the strength of ferrous iron concentration of ferrous iron in both cases are same, since ferrous iron from the same stock are being used. Let us assume normality of ferrous iron be N1. So it will be same in both the experiment, N1. Now assume molarity of potassium permanganate be M. So molarity of potassium permanganate will be same, since the same potassium permanganate solution is used. So molarity will remain same. Normality will change as it depends on N factor, and N factor depends on medium in some cases. So now if M is the molarity, so normality will be 5 times M. N factor is 5. So milliequivalent will now be equal to normality multiplied by volume. That is, milliequivalent of KMnO4 will be 45 into 5m normality into volume, and that will be equal to milliequivalent of ferrous iron, which is 50 N1. That comes from here. This is one relation we have got here from the redox concept. On the other side, molarity is again same, but now normality will be 3m, because in basic medium n factor of potassium permanganate is 3. So normality will be 3 times molarity, and normality multiplied by volume will be milliequivalent of KMnO4. So milliequivalent of KMnO4 will be 3m into x, and that will again be equal to milliequivalent of ferrous sulfate, which is now 25 and 1. This is the second relation we have obtained from second experiment. If we relate these two, we can put here the value of N1 from that relation. So 45 into 5m is equal to 50n1, which can be written as 2 into 25n1. 2 into 25n1, and substitute the value of 25n1 is equal to 3mx from there. So it will be 2 into 3 into m into x. M on two sides will cancel off. 3, 15, 45. So x will be equal to 15 into 5, 75 divided by 2, which is 37.5 milliliter. 37.5 milliliter. So this way we determined that in basic medium 37.5 milliliter of potassium permanganate will be required to titrate the 25 ml of ferrous sulfate solution in basic medium. Now proceed this redox titration with more example so that we can get confidence about redox reaction and redox titration. Ultimately, more you practice, more you learn in this redox reaction, and today we are doing the ultimate part of this redox reaction chapter, which is redox titration. So now let us imagine a situation. Say 1.5 gram of a sample containing Fe3O4 is dissolved in dilute H2SO4 and excess of zinc is added, where all iron got converted into ferrous ion. After filtration, filtrate containing ferrous ion required say 40 ml 0.06 molar acidic KMnO4 solution. 40 ml 0.06 molar acidic KMnO4 solution. Determine percentage purity of original sample considering impurity to be inert. Once again, we have a situation in which a sample of mineral contain iron in the form of ferric oxide, and that sample is first treated in acidic medium with zinc, which reduced all iron to ferrous iron, and the solution after filtration was titrated with potassium permanganate, where potassium permanganate will oxidize ferrous iron again to ferric iron. So from the given information, we have to determine the amount of Fe3O4 ferroferric oxide in the original sample. So let us proceed. What is happening here? Fe3O4 with zinc is converted into ferrous iron. If we conserve the iron, one of this will give 3 of ferrous iron. And then this ferrous iron is oxidized with potassium permanganate in acidic medium, so it will be oxidized to ferric iron, reducing manganese to Mn2+. Titration is occurring here. So milliequivalent of permanganate will again be equal to milliequivalent of ferrous iron. And milliequivalent of potassium permanganate will be equal to its normality, which is 0.06 into 5, 0.06 molar, so into 5 normal, and 40 ml. So into 40, normality into volume, it will be 0.6 into 5, 3 into 4, 12 milli equivalent. Five into 6, 30, so 0.3 into 40, 12 milliequivalent, right? So 12 milliequivalent of potassium permanganate will oxidize 12 milliequivalent of ferrous iron. So its milliequivalent will also be 12. And in this reaction, N factor of ferrous iron is 1. So it will also be millimole. It will also be millimole of ferrous iron, which will be 12, the reason being N factor is 1. Now from this ferrous iron, millimole of Fe3O4 can be known. Here we determined 12 millimole, and since 1 mole gives 3 mole, so 12 millimole will be obtained from 4 millimole 1 gives 3, so 4 millimole will give 12. So now we know the millimole of Fe3O4, and once it is known, mass can easily be determined. So mass of Fe3O4 will be equal to 4 into its molar mass. Its molar mass is 232 divided by 1000 millimole. So mole will be 4 by 1000 into molar mass. If we calculate it, it comes out to be 0.928 gram. And if we convert it into percentage, so percentage mass of Fe3O4 will be equal to 0.928 divided by 1.5 into 100. If we solve it, it comes out to be 61.86%, which is approximately 62%. So with this calculation, we determined the mass percentage of Fe3O4 in the original sample. A precaution must be taken in solving this question. See, if one go through the concepts of equivalence from beginning till end and say that 12 milliequivalent of ferrous ion will be obtained from 12 milliequivalent of Fe3O4, you may find some problem in solving the questions through that way. The reason being, milliequivalent of one reaction cannot be directly transferred into another reaction, because usually n factors differ from reaction to reaction, and concepts of equivalence is related to n factor. So mole is the absolute quantity. It is always better to transform equivalent into mole and then carry it to another reaction, carry it from one reaction to another reaction. Therefore, we have converted milliequivalent to millimole, and then from millimole we return back to millimole of Fe3O4. So this is the way we approach questions of redox titration. Solve some more situation of redox titration. As I said you in the beginning, we are going to do a lot of practice today on redox titration. So as much we can, it will be helpful for us. Let us see a situation . 50 ml of a H2O2 solution. We have a hydrogen peroxide solution. 50 ml of H2O2 solution is treated with excess of Ki solution. Excess of Ki solution. Liberated iodine was titrated using a 0.1 molar sodium thiosulfate solution. 20 ml of Na2H2O3 solution was required. determine mass of H2O2 per liter of original solution. Mass of H2O2 present in 1 liter of original solution. Now H2O2, as we have seen in the previous lecture, act as both oxidizing and reducing agent. In the present problem, H2O2 is being reacted with Ki, which is a strong reducing agent. So definitely H2O2 is an oxidizing agent. So in the first step, H2O2 is reacting with iodide ion, where iodide is converted into iodine, and H2O2 into H2O. And that iodine is being titrated with H2O3 2-, where it reduces iodine to iodide, oxidizing itself to S4O6 2-. We have seen that N factor of H2O3 2- thiosulfate hypo is 1. N factor for thiosulfate is 1 in iodometric titration when it reacts with iodine. So its 0.1 molar is also 0.1 normal, and its 20 ml is required. So 20 ml of this solution will contain 20 into 0.1, so 2 milli equivalent. And 2 milliequivalent thiosulfate will react with 2 milliequivalent of iodine. So milliequivalent of iodine is 2, which comes from here. So milliequivalent of iodine is now known. That can be related to the H2O2. Iodine in this reaction has N factor of 2. I2, 2 is part of formula, so for 1 I2, 2 iodide will have to be balanced, and if we take 2, so 0 to -2, N factor for iodine is 2. So 2 milliequivalent will be equal to 2 by 2, 1 millimole. So iodine is 1 millimole. If we balance this, we know that N factor of H2O2 is 2 and N factor of iodide is 1. So 1 will come here, N factor of this will multiply here, and N factor of this will multiply here. So they will react in 1:2 molar ratio. And if 2 iodide react, 1 I2 will be formed. So 1 mole of iodine from 1 mole of H2O2. So 1 millimole of I2 will be formed from 1 millimole of H2O2. So now we have determined the millimole of H2O2, which is 1 in 50 ml. So using that, we can determine millimole of H2O2 in 1000 ml will be equal to 1000 upon 50, 20 millimole. If we convert it into mass, so mass of H2O2 per liter will be equal to 20 into molar mass, which is 34 divided by 1000 for millimole. So 34 into 268 divided by 100, 0.68 gram per liter. This question could have been done directly through concepts of equivalence from beginning till end also. The reason being, iodine iodide systems are same everywhere. So we could have applied the milliequivalent of thiosulfate, which is 2 is equal to milliequivalent of iodine, which will also be milliequivalent of H2O2. So 2 milliequivalent of H2O2 and n factor is 2. So 2 by 2, 1 millimole. Same calculation would appear. So this is how we proceed in redox titration. Now let us take another situation to demonstrate redox titration further. Let us take a situation. 1 gram of a moist sample. We have a moist sample, means it contains moisture, containing KCl, KClO3 and impurity which is inert, is dissolved to obtain 250 ml solution. To 25 ml of this solution, excess of SO2 gas was passed, where all chlorate reduced to chloride. The resulting solution gave 0.1435 gram AgCl on treatment with excess silver nitrate solution. So in this reaction, there will be two sources of chloride, one from original, one from stock. In another experiment, 25 ml in another experiment 25 ml of the same stock solution, 25 ml of the same stock solution was heated with 30 ml 0.2 molar ferrous sulfate solution. Unreacted ferrous sulfate solution, unreacted ferrous sulfate required 50 ml 0.016 molar acidic KMnO4 solution. Determine mass percentage of KCl and KClO3. A lot of things are given in this question, but its solution is not as lengthy as the question is. Its solution is very straightforward. What is important in this question, that in the first experiment SO2 reduces chlorate. SO2 reduces chlorate to chloride. So some chloride will come from KClO3 and some in original, and both of them will be precipitated as AgCl. In another experiment, 25 ml of the same stock solution is treated with reducing agent, but after reaction some reducing agent is left unreacted, which require 50 ml of 0.016 molar KMnO4. So let us proceed. In first experiment, in first experiment, we have two sources of chloride, KCl and KClO3, but both contain 1 mole of Cl, so both will give 1 mole of chloride. And we can say that the sum of their moles, say if X mole of KCl and Y mole of KClO3 are there, so it will give X mole of chloride, it will give Y mole of chloride. So total mole of chloride will be equal to sum of the moles of KCl and KClO3 in first experiment, and that is equal to moles of silver chloride, and moles of silver chloride is 0.1435 divided by 143.5, it is molar mass of silver chloride, 108 plus 35.5, so 143.5. It is a small quantity, so multiply it by 1000 to get the millimole. It is 1 So millimole of this 2 is equal to 1 in 25 ml. In second experiment, only ClO3 minus is being only ClO3 minus is being estimated. So milliequivalent of this will be equal to milliequivalent of reducing agent reacted with it. But milliequivalent of ferrous sulfate taken initially is equal to 30 into 0.2 for ferrous sulfate. Molarity is also normality since n factor is 1, so it is 6. Milliequivalent of ferrous sulfate left unreacted is equal to milliequivalent of permanganate required after, that is 50 into 0.016 into 5, n factor is 5, so it is 4. So milli equivalent of ferrous ion reacted with ClO3 minus will be equal to 6 minus 4 taken initially left, so difference reacted with ClO3 minus, so 6 minus 4, 2. So this 2 is the milliequivalent of chlorate in 25 ml of solution, and chlorate is being reduced to chloride. Chlorate is being reduced to chloride. So n factor here is plus 5 to minus 1, 6. 6. N factor is 6. So for chlorate we can convert this millimole into milliequivalent into millimole. So millimole of ClO3 minus will be equal to 0.2 divided by 6. So it is, sorry, 0.2 nahi, 2 divided by 6, 2 milliequivalent divided by n factor. So 1 by 3, so 0.33. So now millimole of chlorate is known, and total millimole is also known, and all these are on 25 ml basis. So if we subtract millimole of KClO3 chlorate from 1, that gives millimole of KCl in 25 ml. So millimole of KClO3 in 25 ml we have just determined 0.33. Therefore millimole of KCl in 25 ml will be 0.67. So total millimole in how many? 250 ml. 250 ml will be 3.3 KCl and 3.3 KClO3 and 6.7 KCl. So mass, corresponding mass of KClO3 will be equal to 3.3 into 122.5 its molar mass divided by 1000. If we calculate it, it comes out to be 0.4 gram approximately. Similarly, mass of KCl will be 6.7 into 74.5 molar mass of KCl divided by 1000. This comes out to be 6.7 into 74.5. This is 0.5 gram around. So that will give the mass percentage. So this corresponds to mass percentage of KClO3. Sample mass is 1 gram. So 1 gram contain 0.4 gram of KClO3. So 40%, and mass percentage of KCl is 50%, 0.5 gram in 1 gram, so 50 gram in 100 gram. So this is the way we work in redox titration. Let us do more practice on stoichiometry and redox titration. Suppose a situation is given like this. 0.6 gram of a sample of pyrolusite which contain manganese dioxide is dissolved in 200 ml 0.05 molar H2C2O4 oxalic acid solution. To this solution, excess of H2SO4 was added and diluted to 500 milliliter. So now by adding water, the solution is diluted to 500 ml. 100 ml portion of this solution required 50 50 ml of a 1 by 150 molar acidic KMnO4 solution. Acidic KMnO4 solution. Calculate mass percentage of MnO2 in original sample. Molar mass of manganese is 55. What is this question now? Pyrolusite contain manganese dioxide, and in acidic medium we have seen that manganese dioxide act as an oxidizing agent. So when manganese dioxide comes in contact of oxalic acid, which is a reducing agent, a redox reaction will occur in which manganese dioxide will oxidize oxalic acid, but after dilution, if a portion of the resulting solution is analyzed, it required potassium permanganate solution, which is an oxidizing agent, which indicates that in the previous reaction some reducing agents were left unreacted. The entire reducing agents were not consumed in the previous reaction. So, how to proceed? We have two oxidizing agents in this process, manganese dioxide and potassium permanganate, and one reducing agent which is oxalic acid. If we find out the milliequivalent of KMnO4 required in the final stage, then that would be equal to 50 into 1 upon 150 into 5. Normality will be molarity into 5. So if we solve it, 30, so 5 by 3 milliequivalent. And this is the milliequivalent of potassium permanganate required to react the unreacted oxalic acid. So we can say that in 100 ml of the stock solution, there is 5 by 3 milliequivalent of oxalic acid remaining unreacted. So in 100 ml stock solution, 5 by 3 milliequivalent of oxalic acid is remaining unreacted. But since the stock is 500, stock is 500, so total milliequivalent of oxalic acid left unreacted is equal to 5 by 3 into 5, 25 by 3. In 100 ml, 5 by 3 is remaining, so in 500 ml, 25 by 3 milliequivalent would be remaining unreacted. Now, milliequivalent of oxalic acid taken initially, it was 200 milliliter into 0.05 molar into 2 for oxalic acid, and factor is 2, so molarity into 2, normality, so it is 0.1 into 200, so 20. So initially 20 milliequivalent was taken, out of which 25 by 3 milliequivalent are left unreacted. So milliequivalent of oxalic acid reacted with MnO2 is equal to taken initially minus left, so 20 into 360 minus 25, 35 by 3 milliequivalent, and this will be same as the milliequivalent of MnO2 present in the original sample. So milliequivalent of MnO2 in original is equal to 35 by 3. So mass of MnO2 is equal to 35 by 3 into 1 by 2 for mole. For number of moles divided by 2, n factor is 2 here. So now it is millimole into molar mass 87 divided by 1000 millimole. So mole by 1000 into molar mass. N factor is 2 because manganese dioxide in the above reaction is getting converted into Mn2 plus 4,2 plus 2, so N factor is 2. If we solve it, it comes out to be 35 into 87 divided by 6000, so 0.5075 gram. It is 0.5075 gram. If we convert it into percent, it comes out to be 0.5075 divided by 0.6 into 100. So 84.5%. So this is the mass percentage of manganese dioxide in the original sample of pyrolusite. So this is the type of problems we are going to solve in redox titration. Let us take few more examples of redox reaction used in redox titration. Suppose a situation is given like this. 0.55 gram of a sample of Ki is dissolved in 50 ml 0.1 normal KiO3 solution. liberated iodine is evaporated and around 2-3 gram Ki is further added to solution after cooling to room temperature. After cooling to room temperature. The liberated iodine now required 21 ml. Liberated iodine now required 21 ml of 0.0956 molar sodium thiosulfate Na2H2O3 solution. Determine mass percentage of Ki in original sample. Iodine is 131. Molar mass of iodine is 131. What is happening now? When we add Ki to KiO3, Ki is a reducing agent. Ki is a reducing agent and KiO3 is an oxidizing agent. So what will happen in the first step? Potassium iodide will react with potassium iodate. Ki will react with KiO3 and iodine from both reagent will be converted to iodine, I2. The I2 produced in the first stage is eliminated by evaporation. Now to the resulting solution after cooling, 2-3 gram, which is excess for the present case, 2-3 gram Ki is added. Further iodine is liberated. On adding Ki, further iodine is liberated, indicate that in the first stage KiO3 potassium iodate was in excess. Some potassium iodate was left unreacted, which is now reacting with excess Ki added, giving off iodine. So in the second stage, iodine liberated is due to presence of unreacted potassium iodate. So in the final titration, the iodine is produced from unreacted KiO3. So evaluating iodine, finally we can find out how many milliequivalent or millimole of KiO3 was left unreacted, and subtracting that from the original KiO3 will give the milliequivalent of KiO3 reacted with original Ki, and that will lead us to determination of milliequivalent of Ki in the original sample. Let us work it out. First stage is Ki reacting with KiO3 giving I2 evaporated off. Then KiO3 unreacted, Ki excess iodine, and this iodine is being titrated with Na2S2O3, where this will be again converted into I minus and S2O3 into S4O6 2 minus, that we all know. So milliequivalent of sodium thiosulfate required in the last step will be equal to milliequivalent of iodine produced, and milliequivalent of sodium thiosulfate required in the last step is 21 into 0.0956 milliequivalent for sodium thiosulfate, and factor is 1. So molarity 0.0956 will also be normality. If we solve this, comes out to be 21 into 0.0956. So it is 2. It is 2 milliequivalent, which will react with 2 milliequivalent of iodine, indicating that 2 milliequivalent of KiO3 was left unreacted. Milliequivalent of KiO3 taken initially was 50 into 0.1 5 milliequivalent of KiO3 taken initially 5 milliequivalent of KiO3 unreacted is 2. So milliequivalent of KiO3 reacted with Ki here will be 5 minus 2. Milliequivalent of KiO3 reacted with original Ki is 5 minus 2 3. So this will be the milliequivalent of Ki present in this original sample. So milliequivalent of Ki original is 3, implies mass of Ki 3 into equivalent mass, and then factor of Ki is 1. So it will be 3 divided by 1000 into 166 probably 127 plus 39, so it is 166 into 3, so 0.498 divided by 1000, so it is 0.498 gram. So now we have determined mass of Ki, so we can convert it very easily into mass percentage. So mass percentage of Ki will be 0.498 divided by 0.55 gram into 1000, so 0.498 divided by 0.55 into 1100, 90.5. So it is 90.5% by mass. So it is a case of back titration, where in the first step, reducing agent reacting with oxidizing agent, but oxidizing agent is in excess, which is evaluated by titrating further. Now let us take an interesting case of redox titration, in which we will combine this redox titration with an acid base titration also. We are going to combine this redox titration with acid base titration. Suppose we have a situation which says that 2 gram of a sample containing 2 gram of a sample containing oxalic acid dihydrate, potassium hydrogen oxalate, or better take potassium oxalate only, K2C2O4, and inert impurity. Is dissolved in water to prepare 100 ml solution. 100 ml solution. 20 ml of this stock solution, 20 ml of this stock solution required 30 ml of 0.1 molar NaOH, 30 ml 0.1 molar, let us take 32 ml 0.1 molar NaOH to reach the end point. In a separate titration, 25 ml, 25 ml, better 20 ही रखते हैं, 20 ml of the stock solution required, 20 ml of the stock solution required 50 ml 0.02 molar acidic KMnO4 solution. Determine mass percentage of H2C2O4 dot 2H2O and K2C2O4 in original sample. मास परसेंटेज मालूम करना है. How this analysis is slightly different from the others we have done just now. Here the sample in two experiments are reacting differently. Oxalic acid is a reducing agent as well as acid. So with sodium hydroxide only oxalic acid will react. But with potassium permanganate, which is an oxidizing agent, both oxalic acid and oxalate will react. Both will react. So NaOH titration can directly evaluate the oxalic acid. This H2C2O4 will react with NaOH to give Na2C2O4 plus 2H2O, which can directly be used to find out the mole mass of oxalic acid. Sodium hydroxide 32 ml 0.1 molar. So 32 into 0.1, so 3.2 millimole. And it's 2 millimole, 2 mole reacts with 1, so 3.2 will react with 1.6 millimole. So 20 ml stock solution contain 1.6 millimole of oxalic acid. Same will be the mole of oxalic acid dihydrate also. In KMnO4 titration, both H2C2O4 and C2O4, K2C2O4 will react, giving CO2, CO2, Mn2 plus, Mn2 plus. And oxalic acid millimole is 1.6. Its millimole is 1.6. And as a reducing agent, N factor of oxalic acid is 2. So this into 2, 3.2 millicoulant. And millicoulant of potassium permanganate will be equal to millicoulant of oxalic acid plus millicoulant of K2C2O4. And millicoulant of KMnO4 for 20 ml is 50 into 0.02 into 5 molarity multiplied by N factor. So 5 millicoulant. Out of this 5 millicoulant, 3.2 millicoulant will be consumed for oxidizing oxalic acid. So balance for K2C2O4. So milliequivalent of K2C2O4 will be 5 minus 3.2, so 1.8 millicoulant. And these two are the millicoulant, millimole in 20 ml. So for total millimole of H2C2O4.2H2O, 1.6 millimole in 20, so in 100, 5 times, 1.6 into 5, so 8 millimole. 1.6 into 5, 8 millimole. And total millimole of K2C2O4 will be 1.8 into 5. No, 1.8 is the millicoulant. So millimole will be 1.8 by 2 into 5. So 4.5. So mass of H2C2O4 dot 2H2O will be 8 into 126. Molar mass is 126 divided by 1000. 8 into 126. So it is 1.008 gram, which we convert into percentage. It will be 1.008 by 2 into 100. So 50.4%. Similarly, mass of K2C2O4 will be 4.5 into molar mass. Molar mass of K2C2O4 is 39 into 2, 78 plus 88, 166 upon 1000. 0.747. If we convert it into percentage, it will be 0.747 upon 2 into 100. %37.35%. So that is the way we proceed for redox titration. Now we will be taking two more problems. Which require some extra skill, or I can say that is not as straightforward as we are doing now. So let us take few more examples, two more examples of redox titration that will complete our redox reaction topic. So let us take these two examples to complete this chapter. Let us say a situation is given. 0.5 gram sample containing Cu2S, cuprous sulfide. Cuprous sulfide is dissolved in dilute H2SO4 to make 100 ml solution. A 10 ml portion of this solution, a 10 ml portion of this solution let us take 20 ml for better data. 20 ml portion of this solution is mixed with 25 ml is mixed with 25 ml 0.04 25 ml 0.04 molar acidic KMnO4 solution. After boiling of SO2, SO2 is a product in this reaction. So after boiling of SO2, 10 ml 0.1 molar 10 ml 0.1 molar ferrous sulfate was required to reduce unreacted KMnO4. Determine mass percentage of Cu2S in sample. What is different in this question? Potassium permanganate oxidizing agent when reacts with cuprous sulfide in acidic medium, sulfide here is converted into SO2 given in the question, as well as copper will also be oxidized from cuprous to cupric, reducing manganese to MnSO4. So in this analysis, two elements are getting oxidized simultaneously, that is cuprous ion and sulfide ion. How? Cuprous ion is getting oxidized to cupric ion and sulfide to SO2. To find the N factor, we need to determine change in oxidation number for 1 unit of reagent. And in 1 unit of reagent, we have 2 copper, so we will have to find out change for 2 copper and 1 sulfide. So for 2 copper plus 2 plus 4, so change of 2, for 1 sulfur minus 2 plus 4 sulfur here is plus 4, so minus 2 4, 6. So total 8 unit of change is occurring in oxidation number for 1 cuprous sulfide. So its N factor is 8. This is the important part of this question. So N factor is 8 for cuprous sulfide. N factor of permanganate is known. So 0.5 gram sample of this is dissolved in sulfuric acid to make 100 ml solution. A 20 ml portion of this solution mixed with acidic permanganate, but some permanganate is left unreacted, which required some ferrous sulfate. So for 20 ml, if we perform the calculation, milli equivalent of ferrous ion required is 10 into 0.1, 1, and that will be equal to milli equivalent of potassium permanganate left unreacted equal to milli equivalent of KMnO4 left unreacted. Milli equivalent of potassium permanganate taken initially of KMnO4 taken 25 into 0.04 into 5 N factor, so 0.04 into 5, 0.2, 0.2 into 25, so 5. 5 milliequivalent of potassium permanganate taken, out of which 1 was left unreacted. So how many milliequivalent of potassium permanganate reacted with cuprous sulfide here? 5 minus 1, 4. So 4 milliequivalent KMnO4 reacted with Cu2S. That will also be equal to milliequivalent of Cu2S. But this is the milliequivalent of cuprous sulfide in 20 ml. So total milliequivalent of cuprous sulfide will be equal to this 4 into 100 by 20, so 20. As we have determined N factor of cuprous sulfide 8, so if we convert this milliequivalent into millimole of cuprous sulfide will be 20 divided by 8, so 2.5. So mass of Cu2S 2.5 upon 1000 mole into cuprous sulfide 64 into 2, molar mass of cuprous sulfide 64 into 2 plus 32, 160. So if we multiply, it comes out to be 0.4 gram. And if we convert it into percentage, it will be 0.4 upon 0.5 into 100, so 80%. So the original sample contained 80% of cuprous sulfide. So by this way, we have solved a problem of redox titration in which more than one elements are oxidized simultaneously. Now, let us take one more last question in this series of redox titration. And with this problem, we will finish this chapter here. So, let us take one more question. As I have said, this would be our last question of this lecture. Suppose a situation is given in which 3 gram of a sample containing Fe2O3, Fe3O4 and inert impurity is dissolved in dilute H2SO4 and excess of Ki is added, converted all iron into ferrous ion. Potassium iodide is a reducing agent, converted all iron to ferrous ion. Oxidizing itself to iodine. Oxidizing itself to iodine. Solution is diluted to 100 milliliter. A 20 ml portion, of the above solution required 11 ml 0.5 molar Na2S2O3 to titrate iodine. In a separate analysis, 50 ml of the above solution after removing iodine by boiling required 12.8 ml 0.25 molar 0.25 molar. Acidic KMnO4 solution for oxidation of ferrous ion. Determine mass percentage of Fe2O3 and Fe3O4 in original sample. What is there in this question? We have a sample which contain ferric oxide and ferroferric oxide Fe3O4, and some inert impurity is also there. We dissolved this sample in dilute sulfuric acid and treated with potassium iodide, which is a reducing agent, and it reduced all iron of the sample into ferrous ion, oxidizing itself into I2. By adding water, we diluted it to obtain 100 ml of a stock solution. 100 ml of stock solution. So, after obtaining the stock solution, we did two analyses on the stock solution. In one analysis, we estimated iodine, and in another analysis we estimated iron. Let us see how it works, how we attempt the situation. In first step, it will require some space, so let us use the space cautiously. In first step, Fe2O3 reacted with Ki to give ferrous ion and I2. Fe3O4 reacted with Ki giving ferrous ion and I2. If we assume that the sample contains, say, X millimole of Fe2O3 and Y millimole of Fe3O4. So, in this analysis, N factor for Fe2O3 is how much? Here the iron is total plus 6, 3 oxygen minus 6, so 2 oxygen plus 6. On the right side, if we conserve the iron only, so 2 iron, 2 iron, so 2 into 2 plus 4 and plus 6, so N factor here is 2 plus 6, 2 plus 4. In this, if we conserve the iron, N factor for Fe3O4 is once again 2. 4 oxygen, so minus 8, so plus 8 on 3 iron, and 3 into plus 2 plus 6, 8 to 6 for 1 unit, change of 2. So here also N factor is 2. So we can determine milliequivalent of Fe2O3, milliequivalent of Fe3O4, and then accordingly milliequivalent of iodine can be determined. So if we want to know the milliequivalent of iodine produced in this two reaction, we'll say that x millimole multiplied by N factor 2x milliequivalent will give 2x milliequivalent of iodine here, and y millimole into 2y milliequivalent will give 2y milliequivalent of iodine here. So total milliequivalent of iodine will be 2x plus 2y, and that will be equal to milliequivalent of iodine estimated, and milliequivalent of iodine estimated will be equal to milliequivalent of hypo used up. It will be equal to milliequivalent of Na2S2O3 required, and that will be equal to 11 into 0.5. Be very careful, for sodium thiosulfate N factor is 1. So molarity is also normality. So milliequivalent of sodium thiosulfate will be volume required 11 ml into normality into 5 also. Since it is total milliequivalent of iodine and 11 ml 0.5 molar sodium thiosulfate is required only for 20 ml portion of the stock solution. So for 100 ml 5 times. So it will be 11 to 5 55 divided by 2, so 27.5. So we have found one equation, 2x plus 2y is 27.5. Let us call it equation number 1. It is equation number 1. In the second analysis, we are estimating ferrous ion, and ferrous ion will react with permanganate by this reaction, where ferrous will be converted to ferric, manganese will be reduced to Mn2+. We cannot say that milliequivalent of ferrous will be same here and here, the reason being N factor is different here and here. Here N factor is 1. So it is better we go through mole for calculating ferrous ion here. If we have x mole of Fe2O3, it will give 2x millimole, and if we have y millimole of this, it will give 3y millimole of ferrous. 1 gives 3, so y will give 3y millimole, and total will be 2x plus 3y millimole, but this millimole will also be milliequivalent of ferrous ion, because it is N factor of ferrous ion is 1. So it is 2x plus 3y milliequivalent, and that will be equal to milliequivalent of permanganate. So it will be milliequivalent of permanganate, which is 12.8 into 0.25 into 5, molarity multiplied by n factor of permanganate 5 into 2 also, because this is the volume of permanganate required for 50 ml of the stock solution. So for 100 it will be 2 times. If we solve it, 5 into 2, 10 into 12.8, so 128 divided by 4. It is 32. So we have got another equation of xy. So 2x plus 3y is equal to 32, and this is the second equation. Now this two equation 1 and 2 can easily be solved for x and y. Subtract 1 from 2, x will cancel out, 3y minus y, 2y, y. So y will come out to be how much? 4.5. And see, we have taken this assumption in millimole. So 32 minus 27.5, 4.5, which will give x is equal to how much? If we substitute y here, so 4.5 into 2, 9. If we subtract 9, 18.5 divided by 2, 9.25. So we have got millimole of ferric oxide and ferroferric oxide, which can be converted easily into mass. So mass of Fe2O3 will be equal to x 9.25 into molar mass of this, which is 160, probably 112 plus 48, yes, 160 divided by 1000 for milli. So it will be 1.48 gram. If we convert it into percent, it will be 1.48 divided by 3 into 100. So it is 49.33%. Similarly, mass of Fe3O4 will be its mole Y, which is 4.5 into molar mass (232 upon 1000). It is 1.044 gram. If we convert it into percent, it will be 1.044 upon 3 into 100, 34.5. So this is the percentage of Fe3O4 and this is the percentage of Fe2O3. So that is the way we perform calculation on redox titration, and I think it is more than enough practice to understand the redox titration process. So we'll be discussing one more session. We'll be taking one more session in redox titration and redox process, in which we'll be taking only the problems asked in IIT JEE, past JEE, and some additional multiple choice questions we will be taking into discussion.